Okay, thank you. My name is Shotaro from National Johnson University, and today I will talk about our recent work on fast radio burst host galaxies. And this work was done with TPS2026 here, and also Haruka Kusakabe at Tokyo University, and also Tomogoto here. And this work was recently published in NTHU letter. Okay, let me begin with introduction. Fast radio bursts, or FRBs, are mysterious flashes of radio waves coming from outside our Milky Way. And they actually happen extremely frequently on the sky, 1,000 times per day across the sky. Yet each burst only lasts for a few milliseconds, and it releases enormous amount of energy, around 10 to the 40 eV. And now we know that they are extragalactic phenomena because their dispersion measure, shown here, are much larger than what the Milky Way alone can produce. And this dispersion measure is actually written as an integral of the free electron along the line of sight in the universe. So FRBs can naturally be tools for cosmology. But the most important mystery is still about their origins. They are thought to be related to magnetars, which is strongly magnetized neutron stars. However, the many details remain unclear, and actually the diversity of FRBs suggests that maybe there might be more than one progenitor. And so, to solve this problem, we need to understand not just the burst property here, but also where they were born, namely host galaxy. And today I will focus on what host galaxy, particularly their metallicity property, can tell us. Okay, so this is the motivation. So why metallicity? Because metallicity, I mean the gas phase metallicity. This metallicity actually controls the stellar evolution. It affects the stellar wind and also mass loss and also compact object formation. So by studying directly this metallicity property of the host can tell us clue to their progenitors. So here is a key question I want to address in this talk. So this is the stellar mass versus metallicity of the galaxy. And the normal galaxies are known to have a tight relation between stellar mass versus metallicity, which is called mass metallicity relation. And this is known in galaxy field. And our question is whether FRB prefer higher or lower metallicity environments than normal galaxy at given stellar mass. If there is such kind of deviation, this might contain interesting physics about their progenitor. So we want to address this by just directly looking at the FRB host galaxies. Okay, so here are some problems in the previous works. There has been many work on host galaxy. However, most work only focus on stellar mass versus the star formation rate. However, these two quantities are just a proxy for physics, and it doesn't actually strongly regulate progenitor physics. Therefore, we need to focus on much better quantity, namely metallicity. Second, actually, most studies use incomplete sample. For example, most samples use magnitude-limited galaxy sample to compare with fast radio burst host galaxy, which is actually not complete. Therefore, their result might be biased by this kind of observational selection. We want to avoid this. So basically, to really understand the FRB progenitor, we must go beyond stellar mass and metallicity, star formation rate. And also we need to use a properly controlled pair sample for comparison. Then let me explain the data and the method quickly. So we compiled 49 FRB host galaxies in the literature, and they are all well localized to arc-second localization accuracy to its galaxy. And using our A-scan and also DSA surveys, these are FRB radio surveys. And they have an optical spectroscopy with a large telescope. Then, so we want to measure the same emission lines for every galaxy, including H-alpha, H-beta, oxygen-3, nitrogen-2. This lets us get metallicity in a uniform way. Then how to measure metallicity? This is kind of methodology we chose. So we use strong optical line diagnostics using O3N2 index, which is actually defined by these 4 lines, ratio of these 4 lines. For given FRB metallicity, so for given oxygen, nitrogen value, we can estimate the metallicity using the existing calibration, which is well constrained in galaxy field. This is how we measure metallicity. Then how to select a sample, this is also a very important part. Actually, we first define volume limited sample of fast radio burst host galaxy. So we are not biased towards only bright or nearby galaxies. Then we build controlled sample of the galaxy under exactly the same condition which satisfy this criteria for the fair comparison. Then we directly compare 3 quantities, stellar mass and star formation rate, and most importantly, metallicity of the galaxy between FRB host and the background galaxy. It's so clear. So important thing is by treating FRB host and the normal galaxy in the same way, that any difference we should see should reflect true physics, not the selection bias. Then let's see the result quickly. Okay, here I show the metallicity against the stellar mass. And what I show here by green contour with data point, this is the background galaxy, and this must be compared with FRB. Where FRB locates? It's here, and you can see the data points here. So at the first glance, it looks very different from background galaxy. However, if properly weighted by star formation rate, that this observational, this model goes to the right side as a magenta contour. So now we perform 2D case test between this magenta color contour and the FRB host. Then we found significant consistency between FRB host and the star formation rate weighted background galaxy. This means there is actually no strong metallicity preference in fast radio burst host galaxies. So this is the first time to confirm by using fair comparison in the literature. This is the most important result. Next, actually we also want to look for any kind of deviation in 3D plane. So between mass and the star formation rate and the metallicity. So this figure shows metallicity, but against the linear combination of the mass and the star formation rate. This is projected relation from 3D into 2D, and this dashed line is known relation for a normal star forming galaxy, which is known as fundamental metallicity relation, which applies to any redshift, surprisingly. This is beautiful relationship for the background galaxy, and the FRBs are like this. So this is also the first time to see this in the world, actually. Then we want to compare whether FRB hosts are offset from this normal galaxy. We measure the possible offset. Then we confirm FRB hosts are actually located slightly below this relationship. This is with 2 sigma, so tentative evidence. Okay, so let's discuss our result. So first of all, we found there is no strong metallicity preference in fast radio burst host galaxy. What does this mean? It could mean that FRB do not require special metal-rich or metal-poor environments. This supports models in which magnetars can form through metal-independent formation pathway. Then another thing we can point out is that FRB can actually occur, FRB should exist even in very low metallicity environment, especially in high redshift in the early universe. This is very good news because high redshift FRBs can be used to study the ionization history of the universe, including helium and hydrogen reionization era at very high redshift. So basically, in summary, no metallicity preference actually doesn't mean no physics, but it actually means it opens a new powerful way to use FRB as a probe of the high redshift universe. This is the first implication, and the next I want to briefly look at the metallicity offsets we observed. On the left, we show FRB host offset compared to the normal galaxy. On the right, we show the post-merger galaxy Actually, post-merger galaxies show very similar offset with FRB. They have a kind of negative offset to this relation compared to normal galaxy. What does this imply? This might imply FRB host might be a potentially post-merger galaxy dominantly. In this case, a possible interpretation is that first, I think the FRB host, FRB progenitor stars can be formed during a galaxy merger. Then FRB themselves appear much later after those stars evolve, within a few hundred mega-year up to 500 mega-year. So this is the possible interpretation. The connection might be searched in the future. Okay, so this is the quick summary. So most importantly, we pioneered a study of FRB host metallicity with a good sample and fair selection for the first time. And our takeaway message is that FRBs can be unbiased probe of galaxies and cosmology. And if I have some time, so what's next? Actually, what we measure in this work is actually global metallicity, average metallicity of the galaxy itself. However, the future direction could be look at the exact location of the FRB using 2D spectroscopy and measuring the metallicity at the FRB location. This is much important. So this is actually done with our summer school students, Sherry and Ryan. They are doing independent work right now. So I hope to show their result with them in the future at the conference. Thank you so much.
Hi, Shotaro. Could you go to the slide number 8, please?
Number 8.
So, thank you for the showing the future work. I was wondering, like, if you do the IFU, as you would expect, what could be the, how tighter could be the relation? Do you have any idea for this? Maybe whether your p-value changes in future if you do a better spectrum, I mean like IFU to figure out the metallicity lines.
That's a very good question. Yeah, actually, it depends on how metallicity gradient behave for each galaxy. And some FRB occur at the center, but some of them occur at the very kind of edge of the galaxy or even outside the galaxy. So we could see more deviation for individual hosts. So actually, I can't predict right now, but we should see if we see some interesting, much tighter trend here or deviation. This will tell us about new maybe information. So I can't answer right now, but it's very good thing to think about.
So another question is like this global versus local argument. Is it enough to explain the scatter in the metallicity regime, or do you expect any other mechanisms that could explain the scatter?
No, actually, we haven't measured such scatter. So, so I know what you mean. So I think the scatter could be maybe in the range of maybe maybe less than 0.3 dex for typical massive galaxy. So maybe that could be enough to explain the scatter, global scatter. But I can't tell the right answer right now.
Very nice slides. I want to ask that since you mentioned in the start that FRB is progenitor, and then later you discuss about FRB as probes. So there are two different things. One is FRB progenitors, and other is using FRB as a probe. So what is your main motive of this work in these two aspects? Which you are focusing more regarding the progenitor or regarding?
Actually, both. So, for example, if we see unexpected deviation from normal galaxy, this itself has huge implication for physics, progenitor. However, we didn't see any deviation, strong deviation. That's why I'm now thinking very positive about the use of FRB as a high redshift probe. So actually, at the beginning, I was open to any possibility, but after studying this, it turns out there is no strong deviation. So I'm now focusing maybe both. And so am I answering your question?
Yeah. Can I ask one more?
Sure.
Yeah, sure. Just one more question is that the normal, the first thing you said in the start is that FRB is related to star formation rate, and more star formation rate means more stars, more dead stars, and more FRBs basically. So does their results deviate from this normal assumption that higher star formation galaxy means more FRBs?
Actually, no. Our result is consistent with a global picture of the star forming history. So FRB tend to happen in high star formation rate region, galaxy. So it is consistent with such picture, also seen in other planets. Thank you for your question.
We have to close the session. Thanks to